Hello everyone and welcome back. So this time we'll be talking about beam deflections because we've made it all the way to chapter 10. And as a note, we're going to be going through the entirety of chapter 10 in this video. So if you need more examples or you need to see more done, please feel free to ask. So let's jump right into it. First off, why do we care? Well, let's look at this gymnast right here. They are on the beam. They're about to spin around it. And you know, you've seen it before, that when they do that, this beam is going to bend. It's going to bend quite a bit because it's fairly elastic. Well, all beams bend. All beams bend when we apply a force. So most of the time, it's just very small. Like you stick your hand on a metal beam, it is technically bending, even though it might be infinitesimally small. You're causing a deflection in that beam. So the big thing we need to do is figure out how much is a beam going to deflect, which is bend downward under the force, underneath a particular load. So let's see if we can figure that out today. Okay, first off, we need to develop a coordinate system. And the weird thing is, if you look right here, it looks kind of like we have two vertical components. However, that's not the case. X is still our longitudinal axis. V is perpendicular to the longitudinal axis. Okay? It's perpendicular all the way across. So V is always going this direction. Y, on the other hand, is only for an individual cross-section. So when you start looking at a cross-section of the beam, well, then you're not talking about V anymore, you're talking about Y. Okay? That's important. So please remember that Y is just for the individual cross-sections. V, which is the deflection coordinate system, is for all of our deflecting bending beams. Okay. So we remember from chapter 8, we developed a moment curvature relationship. We said that when we apply a moment, it's going to cause this to curve. And that came, we had the kurtosis here, we had our radius of curvature. And that was all related to the internal bending moment over the modulus elasticity times moment inertia. But it wasn't super helpful back then, but now we're going to bring that back, and it's going to become very helpful today because we're going to now generalize it. Before, it was just a very simple equation. Now we're going to say, okay, what is my general expression for the kurtosis or the radius of curvature for a beam at every single point? And it's this right here. And even though this is a video, I can already hear screaming. So I want you to know that it's not too bad. It's not actually terrible because this term right here is usually very small. And for this course, we're going to say that it's small enough that we can neglect it. Now, if you're like on a diving board or something rubbery, you can't get rid of it. But for metals, it's usually the slope is small enough you wouldn't have to worry about it. So with that, we can then say, okay, simplify things out. My kurtosis, or my radius of curvature, is going to be equal to the second derivative of the deflection. And then this is what's often going to lead to what's called the differential equation of the elastic curve. So if we know what our moment is as a function of x, we can then integrate or take derivatives to get everything else we want to know. So this equation right here, this is key because in most of the problems, you start by getting the equation for the moment. You get the equation for the internal bending moment for a section, and then you can integrate up to get your deflection. Now please remember, sign conventions. Positive bending moment makes it smile. Negative bending moment makes it frown. I know that seems silly, but it's one of those things that we have to keep on harping on over and over again to make sure you don't miss it, because if you do, you're going to get the problem wrong. So let's get it right and not have to worry about that. Now let's look at how those derivatives are related. First off, deflection. This is just how much it's gone from its original unbent position. How far down has it gone? Well, the derivative of that, how much the deflection changes with the longitudinal axis, is going to be equal to our slope, which is often shown with a theta. Then we come to our differential equation of the elastic curve, which helps us relate our moment to our deflection. If we keep on going down, we get our shear, which is the third derivative of our deflection. Then finally, our load, which is the fourth derivative of our deflection. Woo!
So all the way down here, and you can see that we can either take derivatives to go down or take integrals to go up depending on what we know. As a note, there is a whole section in this chapter that's based on the discontinuity functions, which is where you can have a single function that goes over the entire beam. We're not going to be going over that because they're not really used all that often. However, if you want to check that out, you feel free to do so. Okay, so if we look at this, we can also see how these are all related. Okay, they're all related. So if we start at our load, we can develop a shear diagram from that. If we integrate from our shear diagram, we can find our moment diagram. If we integrate and multiply by that little factor, we get our slope diagram. Integrate again, we get our deflection diagram. So we just keep on integrating all the way down until we get what we need. And all is glorious. So, we're going to stop there for today. I believe, let's see, yes. Oh, nope, a little bit more to go. We still got our constants of integration. Now, hopefully you remember from calculus, if you take an indefinite integral, you're going to have issues because we're trying to usually get an equation for the deflection over the entirety of a beam or entire beam section. And so we have to know, we have to do indefinite integrals. Now when you integrate, you're going to start getting constants. And you're going to have to figure out some way to get rid of those constants. And the way you get rid of them is through knowing the end conditions or boundary conditions or other conditions in your beam. So the known conditions that you can use are right over here. There's a lot of them. So just use this as a reference. The big thing to think about is that at a support, your deflection is 0. At a free end, the moment is 0. And at a fixed support, the slope is also 0. Okay? Now, if that's not enough to solve everything, you might have to use symmetry conditions, where maybe you know what it is on one side, and you're saying, well, this is one beam, it can't be all crazy. So even though there's like a discontinuity here, I know that the slope on either side of that has to be the same. Has to be the same, and the deflection at that point has to be the same. So if I know what it is over here, I know what it is over here. Okay, so that's it for this time. Thank you all so very much for listening, and next time we'll jump into the end of the chapter. Like, whoa, yes, it goes really, really quick, but don't worry, we're going to do plenty of examples of doing this analytically and with some numbers too at the end. So next time we're going to jump into what's called the superposition principle to make things a little bit simpler. So have an absolutely wonderful day, and I'll see you all next time. Bye-bye.